So I'm here to talk about the halfword virtual machine and give you a little insight in how the virtual machine works. So the halfword heap emulator, or the halfword virtual machine, is a variant of the usual Beam machine. And the Beam virtual machine you've heard about plenty of times. It's Björn's or Bogdan's Erlang abstract machine. And it works in a way it has done since Bogdan started to implement it, I don't know, before I started at OTP, which is a long time ago, and has evolved over the years. It's a virtual register machine. It's not a stack machine, which people tend to think it's a little bit strange, but that's the way it is. And it has garbage collection per process, you know all these things. And constant pools are added to the virtual machine like two releases ago, so on. One of the things with Beam is that you have this heap, or the generational garbage collector, with two heaps and some extra nurseries, and then you have these large binaries, which are binaries that are, this is very loud, I'll move that down, binaries that are larger than 64 words, and they are stored elsewhere, so to say, not on the heap. So they are stored in separate, like mallocked areas with reference counting and shared among processes. Okay. So if you look at the virtual machine code, or if you look at the subdirector Beam in the source code, you will find a lot of source files, of course, and if you look into them, you will see one data type that's like everywhere, and that's the E term. And an E term is the C view of an Erlang term. And it's like a word large, the size of a void pointer or something. And everything is like an array of E terms. So the heap of a process, or the heaps of a process, is just an array of E terms. And the stack is an array of E terms, and so on. The registers are E terms in the virtual machine. The code is not E terms, but everything else is. So if you construct a complex term in Erlang, you have, for example, a tuple. You allocate, like a tuple of 2 elements, you allocate 3 E terms on the heap, 1 for the size of the tuple and 2 for the elements. And then on the stack, you will have a pointer to the heap where the actual tuple is. And the pointer is an E term. And the contents of the tuple is an E term. So if you look at the code, it's like untyped. So if you look at a BIF, for example, contrary to a NIF, which has these structured types and things like that, if you look at a BIF, it takes like a couple of arguments, or an array of arguments, which is the parameters to the function when you call it, and they are all E terms. And then it does all these things with E terms. There's macros, there's things to allocate data from the heap and so on, but it's all E terms. And then you decode these E terms into normal variables in the C code. So the actual virtual machine loop, if you were here when Lucas spoke earlier, he talked a little bit about how it schedules things. I'll talk a little about what's happening when you actually have a process that you've scheduled and you're trying to run it. So the loop, it's a normal forever loop, going around and finding processes. So it's called a function that's called schedule, which gives you a process to execute. And the process, well, the current process is a pointer in the loop to a structure, which is not all that large, actually. But it contains some things. It contains a reference to the Beam code, to to execute. Either you have like just started the process, then you tell it which module, which function and arity, or you're executing, so you have some other way. But usually when you're scheduled in, you always start at the beginning of a function. So it's not really a pointer to the Beam code in this state, it's a reference. But it also has a pointer to the stack. Of course, it has a pointer to the beginning of the stack or the end of the stack, whatever you want to call it, and to the stack top. So the virtual machine loop digs up the process structure, it digs up the stack top to start executing. And on the stack, there are terms, and that's the variables in your program. That's always there on the stack or in the registers. So, and all these terms, they refer to the heap, where the actual data is stored. So you have the stack top, which the VM loop gets, and you have the heap, which the VM keeps in some way, and you have this reference to Beam code, and the VM loop picks that up as an instruction pointer, where to run. And then you have the registers, which also is an array of e-terms, which is pointers into the heap. Also, you have on the stack, have this really lousy remote control. Oh, you also have those binaries then. They are outside of the heap. So on the heap, you will find structures that point to these binaries. But actually, from the stack, you don't point directly to the binaries. You point to the heap, where it's a structure telling you this is a binary and it's off heap. There's also binaries that on a heap and so on. It could be, yeah, there's a lot of binary stuff. And on the stack, you will also have, and this is a little bit problematic, you might have, or you of course have, return addresses. So when you execute, you usually want to go back somewhere. So you have those return addresses, and they are pointers to code, and code is not Erlang terms as it is constructed. There's another type of pointer. So you, from the stack, you have to be able to point out code, you have to be able to point to the heap, but not directly to the binaries. Okay, that's how it looks. But of course, it's a dynamic language, so, oh, ets data, forget about it. Okay, it's a dynamic language. So ets data is no problem in this context, because ets tables are like elsewhere, and they're referenced by numbers, not pointers or anything. So they're like a database stored some other place. So we have this dynamic language, and contrary to C, for example, which is a little bit dynamic because you can do like anything, but you don't know what data. If you take like one word from the C stack and look at it, you have no idea what it is. It could be like part of a string, or it could be an integer, or a floating point, half of a floating point number, or whatever. But in Erlang, everything is tagged. So every item on the heap or on the stack has a tag telling you what this is. So if you have a variable and asks, have a guard telling you, is this an integer, is integer, you only look at the exact, the variable itself, the word, with the integer in it, and you see this is an integer. And this is done by a little trickery. Each pointer I have shown here points to a word boundary. So in a 32-bit machine, that means you have 2 zeros at the end of the pointer. The least significant bits are always 0. They are used to point to characters inside a word. So we use those bits for a primary tag. And if those bits are 0, this is like a normal pointer. And that means it's a return address, a continuation pointer it's called in the code, but a return address. If it's a 1, it's a console, that means the beginning of a list. And if it's 1, 0, it's boxed, and that means the data is stored on the heap, but you don't really know what it is yet. It's not a list, but it's a tuple, a floating point number, a big number. That's numbers that are too large to store in the word, and so on. So, and if it's 1, 1, the last bit, it's an immediate. So that means it's not a pointer. We have stored the value directly into this word, the e-term word. So on the stack, you might find all these types of things. Either if it's a console or a tuple or something, it's a pointer with a tag on it, or it can be immediates, like local PIDs are immediates, small numbers are immediates, and so on. Atoms are, of course, immediates. So then you go, and the next step is to have even more tag bits for the immediates. And here we can use more bits because this is not pointers. So we limit the amount of values we can have in the word by using more bits. So we have the tags of 4 bits, all ending into 1s, of course, because that means in the primary tag that it's an immediate. So we have a hierarchy where we have immediates like PIDs and ports. They have only 4 tag bits, and then we have immediate 2 tag, which means it's even more tag bits, and so on. And small numbers only have 4 tag bits, which are all 1s, and that makes it easier to, we actually use arithmetics instead of shifting to get the value from it, which is faster. So, and then on the heap, the boxed has a header word with a tag, once again telling you which type of boxed value this is. So it could, if it's all zeros, it's the tuple, and that's the most usual type, of course. And then you have these 26 bits if it's a 32-bit machine, 26 bits for the arity. And the arity is how many words will follow. It's not actually, I mean, a floating point number, 2 words will follow in a 32-bit machine, and so on. It's not like always the arity of a tuple, but for a tuple, it's exactly that number. And these boxed values, they are all these more stranger data types. But if you're in your code write is tuple, for example, you look at the stack. If A is on the stack, capital A, and you write a guard when is tuple A, the virtual machine has to look first to see if A, which is on the stack, if this is a boxed. If it isn't, then it fails. It's obvious. But if it succeeds, this is boxed, then it has to follow the pointer, untag the pointer, follow the pointer down to the heap, and look at the header word on the heap to see if this is tuple. So guard tests for tuples are a little more expensive than guard tests for lists, for example. So if we create a term then, a little fast example, we have this capital A, and we match, we don't assign, we match it to this tuple of 2 elements with a list of 2 atoms and then a number, a small number. Then if you wrote this in your code, you will get a constant and nothing would happen. But imagine that you actually would have to build this. Then what you do is on the heap, you start from inside out. On the heap, you will put the last console consisting of the atom B, which has this tag. I could go back if I had a good remote control to show you. That 001011 is the tag for an atom. And what would be in the rest of the word is the atom number, which then refers to a table where the atom names are. So, but they are unique. I mean, the atom B would always have the same atom number for as long as the system lives. And the second part of the console is nil here because it's the end of the list. And then we build the first part of the list, which is the atom A followed by the tail, which is the next console beginning with B and ending with nil. So this is just like Lisp, car, and coder lists. This is how all functional languages having lists build it. Not all. Actually, some build them with tuples or other things, but okay. So then to build the tuple around this, we put a header word with the arity to the tuple tag on the heap, which is all zeros, and then the next two elements, the following two words will contain the elements of the tuple. So the first element is a console, a cons pointer to the A, and the second one is the immediate number 3. And then on the stack, we put the actual A, which is a boxed pointer. So whenever you follow these pointers, you remove the tags, of course, but it's just masking them away. You don't need to shift anything. So that's how it works. So when you shift from a 32-bit virtual machine to a 64-bit virtual machine, you have to change the size of the term because it's pointers. So everything then grows to twice the size. And if you run a program on a 32-bit virtual machine and then moved it to 64-bit because you had, oh, I need more than 4 gigs of memory. So I moved to 64-bit architecture and I need more than 8 gigs of memory. That's what happens, more or less. Because every data, every piece of data in your program blows up to twice the size. And the horrid thing is like strings. They're already really memory consuming, and now they're twice the size. So a string encoded in a binary, say it is a Latin 1 string, it takes as many bytes as the number of characters, but in the 64-bit virtual machine it takes like, what is it, 16 times more. That won't make you happy, but that's the way it works. So this is obviously a problem. I mean, the problem of strings is larger than what this machine can do, but the problem of using, I mean, like, okay, I had the money to buy this 64-bit architecture. I also have the money to buy 8 gigs of RAM because I can also buy 100 gigs of RAM and still run. Okay, but the problem is the bandwidth problem. I mean, CPUs get faster and faster and faster, and memory gets a little bit faster, but not as much as the CPUs. And if you saw Kosti's presentation here with his 64-core machine and my analysis of his graph there when he tried to run dialyzer in parallel and so on, dialyzer is memory intensive, and he has these small caches, he has a memory bandwidth problem. And almost every application I've seen running on machines like that, especially on Opterons and so on, have this memory bandwidth problem. It's a NUMA machine too, so the memory can be a long way away, and yeah. So twice the amount of memory means more or less twice the amount of memory bandwidth problems. So if you run, you have this CPU, the x86-64, and run it in 32-bit mode, you will, in an Erlang application, get half the amount of memory accesses, half the amount of memory going over the memory bus. And actually, of course, you have caches and things like that, but if you blow up the memory usage to twice the size, you also you will exhaust the caches much faster. So you actually get a lot of memory going through and forth through the memory bus. And the memory bus is slow. And the i7 has a much faster memory bus and then the architecture, the Core 2 architecture. But this is like what Intel tells. If you ask Intel, they say, oh, that's a one-time gift. That won't happen again. So what will happen is that i8 or whatever will be even faster and the memory will still be like not keeping up. So actually running in 32-bit mode is faster. Looking at the Erlang VM doing some benchmarks, which is partly the same benchmarks as Costis has run. But now we're not looking at SMP performance. It's actually SMP virtual machine, but okay, and the blue one is 32-bit, and except for E-stones here, more is better. More is worse. Okay, less is better. Yeah, except for E-stones. So the 32-bit virtual machine is faster on the big benchmark, which has a lot of big integers. On the codec and the code benchmark, the hack bench, the random benchmark, the storage benchmark. Okay, the 64-bit virtual machine is a little bit faster on live, which is more of a number crunching application. And you have twice the amount of general purpose registers and so on. So, because when you run a 32-bit legacy mode, you only have the old x86 registers. So you can benefit a little from more registers and so on. On E-stones, which is also actually a little bit of number crunching application and also an application that doesn't consume a lot of memory. The 64-bit virtual machine is a little better because more is better on that one. So changing from a 32-bit to a 64-bit machine means losing performance, and that's not what you wanted, probably. But you may have to do it anyway because you need the memory, or the memory, like the address space, actually. Okay, so the alternatives are, of course, to stick to the 32-bit machine and rewrite your application, so you split it over several nodes or something. That might be the fastest way, the fastest, so the best performance solution, as long as you don't take into account the hassle of rewriting your application. So, yeah, and you can also buy a lot more memory and a really fast CPU, and don't mind that it's actually slower than it would be if you can run in the 32-bit mode. But it's not, often it's not even possible. I mean, if you have an embedded device, you can't just like, you put a lot of money into development of this custom hardware, and you can't just cram in more memory or more. And the memory of a lot of the embedded devices is quite expensive, actually, and wired to the board. So we thought, and we're not the only ones. The Java people have looked into this problem too, and they have a type of solution in the JRocket, which is more elaborate. They like have more money and they're a lot cooler than we are. But a lot of people have looked into this, and the memory bandwidth is actually a very easily identified problem for the virtual machines. So, so we looked at a couple of solutions ourselves, and the solution that we've heard before in other contexts is why, if this is an array, the heap is an array of words, why don't you just index into it? Why do you have to have pointers everywhere? And That's a good point, but the thing is, it's not only one heap, so it's not one array. It's like several arrays, so you have to know which array and the index into that and so on. So that will require a huge rewrite and possibly a performance degradation that we wouldn't want. And another idea, which was my first idea when I looked at this, is if we have this humongous address space, we could give like 4 gigabytes of virtual address space to each process. And then we have like segmented memory, like in the old DOS world. so this process lives in this segment, this 4 gigabytes and so on. And some elaborate fiddling with the virtual memory, and we would be good to go. And that would have worked, or it might work in the future, but right now a 64-bit processor has 48 address bits, not 64. So the part in between is non-addressable. So there's a lot of bits you can't use. So you have 48 bits, but you actually have 47 bits, and then you pull out 32 bits, and you have 15 bits, and that's less than you need for an Erlang system. You can't have only 15 bits for processes. I don't know how many that would be, but when I counted, it was far less than you could have today. That would limit the number of processes. But we could do things with that, like share segments and then move processes and so on. And that might be a future solution. But the simplest solution, and one that fits a lot of situations, is to simply say, okay, let's pretend this is a 32-bit machine when it comes to processes. So all process data, like heaps, stacks, and actually code because of the pointer from the stack to the code, we put them in the lower part of the virtual memory, of the address space. And everything else, like ETS tables and binaries, shared binaries, and so on, we put them elsewhere, in the upper part, so to say, of the system. And this is, it sounds complicated, but it was really easy to do, simple to do, actually. What we did was, well, ETS was not all that simple, because we had to do something else with ETS tables, because the data in ETS tables is also Erlang terms. So in that case, we actually use this array view of things. So ETS objects are arrays of Erlang terms, and the tagged pointers are actually offsets from the beginning of the ETS object. So we changed the implementation for ETS for this virtual machine, and then we wrote a little wrapper around the mmap that use map no reserve, which is like saying, I want this piece of address space, but I don't want the memory. And allocated the lowest 8 gigabytes of memory address space. And then whenever someone tries to allocate heap, which is easy to identify because this Earth's alloc macro is where you allocate memory, and you actually tell that it's the type heap I'm allocating. So we could just route that to the mmap wrapper, which had this address space, and then just mapped memory pages in that address space and gave it back. So memory allocation to solve that was like implementing the really naive one page at a time memory allocator. And we needed to truncate the pointers, of course, and you add tags. You have a pointer to data, and then you add a tag, and then it's an Erlang term. What you did now, what we do now is you add a tag and throw away the most significant 32 bits, which are zeros, and then you have an Erlang term. And that cost almost nothing. And when I say almost nothing, I mean it. It's like, I couldn't measure any impact on that. And then you expand, when you remove the tag, you expand it to 64 bits, which is like a move. So, no problem. So, how it looks when you run this virtual machine, you have the lower part of the memory, the lower 4 gigabytes of memory, and there we have all the code, the stacks, and the heaps of the processes. Binaries, ETS data, and whatever else we need is up there. And ETS data, usually in telecom systems, they make up like 80, 90, up to 95% of the memory in the system. And it's like ongoing calls, things like that, a lot of data in ETS tables. And you have mnesia tables, well, that's ETS tables. So a lot of the memory in a lot of applications is actually outside of the process heaps. So a lot of applications, not all, of course, have no problem fitting their processes in this low area. So processes and code, and actually you have more than, for the 32-bit virtual machine, you have all these other funky stuff in that memory range. A 64-bit process in Linux has most of the funky stuff up there where the tigers are on the picture. It's actually tigers. and there you have some data sections down there, so you need to be a little bit careful. I sound like you just allocate the memory and you're okay. You have to be a little bit careful. So ETS we solved by this array approach. So we have a special copy function that goes from the array approach to the lower part of the memory approach when you copy from the ETS table to the process heap and so on. Some operations like matching in ETS tables, like the match specs and so on, they were a little bit more tricky, but it was solvable. So if we compare this half-word machine, which is what we call it, the yellow one here, where less is better, it's less than the green one, at least. Almost, yeah, everywhere. And it's almost as fast, or sometimes even faster than the 32-bit machine. So it's better than the 32-bit machine when it comes to number crunching, for example, but not as good as the 64-bit machine. I don't know why, for example, life is not better here. It's something else. It doesn't have anything to do with bandwidth, obviously. But if you look at the codec, for example, where the 64-bit, the memory bandwidth was really a problem for the 64-bit virtual machine, the half-word virtual machine is as fast as the 32-bit. It's nearly as fast as the 64-bit virtual machine on Eastone. So all things considered, it's like the fastest virtual machine we have. And it can break the 4 gig barrier as long as you use ETS tables and things like that. Of course, you shouldn't use ETS tables all the time, but I mean, a lot of the data is data store oriented. So then it's okay to use hash tables. So it's fast. And also, what you don't see on these charts is it takes no more memory than the 32-bit virtual machine. So the ETS data that is stored elsewhere is also as small as for the 32-bit virtual machine. So you can actually store vast amounts of ETS data with this machine. And you won't waste memory in the same way as with the 64-bit virtual machine. Okay, what's lost then? We gained a fast machine, but if you compare to a 32-bit virtual machine, you of course lose the possibility to run on anything else than Linux. Last time I said I will port this to Mac OS, for example, but maybe I'll port it to FreeBSD, but Mac OS is a little tricky, so it might take some time to do that. But of course, you can't run it on a 32-bit Linux either. It's a 64-bit executable. And Hype is still not ported to this one. It's not like really hard to do because it's just the same backend as for the 64-bit machine. But you have to take into consideration that you don't have full pointers and things like that. So, but for now, Hype is not working. And if you compare it to a 64-bit virtual machine, you can't break the 4 GB barrier for process heaps, of course. So if you have an application with like 8 GB of process heaps, there's no way you can use this implementation. Actually, there are products out there which couldn't live with one process being limited to 4 GB of memory. That's a little bit terrifying to think about that, but that's true. So those applications, they can't use this. And of course you lose Hype now. But for all other applications, and even for applications that does not have a problem with the 4 GB as it is now, but run on a 64-bit machine, they can use this halfword machine, and it might gain you some performance. And it's like easy to try. You just configure -- enable halfword emulator. I think it's there. And unfortunately, disable Hype. And then build on Linux, 64-bit Linux. And then you run. You do nothing else to your code or anything else. And it probably works. Yeah. But of course, there's application where this doesn't work. But it's an option. And we have like a couple of people using this now, but it would be nice if more people tried. And if there are bugs, it's tested like every other virtual machine. So it's tested like on 4 different machines each night, and we ran all the test suites and so on. But of course, more users means more testing. And if a lot of people like this and can use this, we can also improve it, maybe by doing what I talked about earlier, having segments for processes, so we can break the 4 GB barrier for the processes as a whole, at least. So please try it out. It's in the main distribution. It's actually supported internally at Ericsson, and so it's as supported as any other Linux, Windows, Solaris, or what else do we support? That's it, I think. Linux PowerPC thing, where we distribute binaries to Ericsson. So this is quite a stable machine. So I would please try it and give me feedback if you find anything strange. Any questions? Yeah?
What about NIFs and port drivers?
Yeah, they're like this 64-bit.
But do they
you have to
not to allocate out of the 4 gig?
That's not a problem, because even if you use like external libraries, the low 4 GB, I've reserved them. So other memory allocators will jump to higher memory. But you have to recompile the NIFs because of the E-term size changes. But it's a completely normal 64-bit DLL or shell library.
So if you're holding a lot of data in your NIFs,
yeah,
you're not subject to this limit?
No.
Okay.
No. You're free to use the rest of the memory. Okay. Any more?
All right.
Okay.
Thank you very much.
Thank you.